Hello everyone, welcome to Mechanical for Gate. So in this lecture we will start our new chapter, that is buoyancy and flotation. So if we talk about buoyancy and flotation, there are certain basic definitions that will be required in your complete chapter, that you mention them here. Like basically certain points here. So first point, let me mention it. So first point states that whenever a body is is either partially or completely submerged or completely submerged in a fluid is whenever a body is either partially or fully submerged in a fluid is going to or it is going to fluid it is going to experience a net resultant force in upward direction. Okay, and this force is known as buoyancy force. Okay, or we also call it like buoyant force. Okay, now second point, if I talk about the magnitude of this buoyant force. So the magnitude of buoyant force is given as weight of the liquid or weight of the fluid displaced and this is basically your also known as your Archimedes principle, or let me like mention this point in Archimedes principle only. Okay, if I talk about next point here, now this buoyant force, if we talk about, so as I mentioned earlier in this point, that upward direction, the resultant force of upward direction is acting on the body. Okay, so the force which lifts the body is known as buoyant force. Okay, and tendency of immersed body immersed body tendency of immersed body to be lifted up is known as buoyancy. Okay, so this is your difference between buoyant force and buoyancy. Okay, now let's talk about your Archimedes principle. Archimedes principle. Okay, sorry. Archimedes principle. Okay, so if we talk about Archimedes principle, so as I mentioned earlier, this is that magnitude of this Archimedes principle tells us that magnitude of buoyant force is equal to the weight of the fluid displaced. Okay, so I can write that Fb is equal to weight of fluid displaced. Okay, and this can be written as equal to your density of fluid into G into volume of fluid displaced. Okay, and we can also write this as Fb is equal to density of fluid into G into, now a volume of fluid displaced can be also mentioned as volume of body submerged. So this body submerged volume can be for both submerged, okay, can be both for partially or fully submerged bodies. Okay, so this is your buoyant force. And if we talk about direction of buoyant force, so next point in Archimedes principle is or we can talk about general point. So this is your point of application of or direction, this buoyant force always acts in vertically upward direction. Okay, and what else? The point of application, if we talk about, so point of application of buoyant force is known as center of buoyancy. Center of buoyancy also. Okay, and it lies on centroid uh, of or centroid, or basically I can say CG, or center of gravity of volume of fluid displaced. Okay, now this volume of fluid displaced or volume of the body submerged can be both. Okay, so I hope you get this point. So this is your Archimedes principle, or Archimedes principle you also call it. Now let's say if I want to let's say derive this how this Archimedes principle came into picture. Okay, so I won't be telling you the story of Archimedes and the king and the gold crown. Okay, That I think you should already know about that. In this I will talk about how this formula come. Okay, how to derive this formula. So let's consider a free surface. Let's say that this is a free surface. Okay, and we have placed a body inside this. Let's say this is a cylindrical body we have placed. So this is your upper surface, is cylindrical walls, and this is your bottom surface. Okay, let's say that from the free surface to the top of the cylindrical cylinder we have a height h1, and from here to here we have height h2. The cylinder has the height of h2. Okay, and the area of cross section is a, let's say. Okay, so what I can say that, okay, and here all over there is water. Okay, okay, so there will be different type of forces acting on the your cylinder. Okay, so if I talk about the cause of your buoyant force, so your buoyant force is caused by increase in pressure with depth in a fluid. So due to the increase in pressure with the depth, we we observe the your buoyant force. Okay, so in this figure if we talk about, so let's say here the pressure is P1 and here your pressure is P2. Okay, so if these are pressure P1 and P2, so I can write here my P1 is equal to rho g h1. Okay, and my P2 or my P2 is equal to rho g times of h1 plus h2. Okay, so if I say that the force due to pressure P1, so F1 downward force on the upper surface, that is your, or let me say that this is point 1 here and this point here is point 2. Okay, so I have written P1 P2. If I write F1 F2, okay, so this is your F1 in downward direction, F2 in upward direction. This is P1 into A, that is rho g h1 times of A. Okay, and here this will be F2 is equal to rho g times of h1 plus h2 is pressure times of A is your force. Okay, now we know that due to the difference in these two forces we will have a buoyant force. So I can say that F buoyant will be equal to F2 minus F1. We can say that F2 is here, F2 value is greater than that of your F1 value. Okay, so this net upward force will be your buoyant force, is your buoyant force. So this buoyant force is equal to F2 minus F1. If you substitute the values here, so this will become rho g. Now here H2 minus rho g will take common. Now H1 plus H2 minus H1 will become H2. Okay, and this here, this term A times of H2 is the volume of fluid displaced. So what I can write? I can write my buoyant force is equal to rho g V. Okay, density time of acceleration due to gravity times of volume of fluid displaced. I hope you get this point. So this case which we have studied here is basically a case for your for your submerged bodies. Okay, this is your buoyant force on submerged bodies. Buoyant force on submerged body. Okay, this is your, okay, so let me move it upward. Okay, now So there are few points I would like to mention here. So now here, if we talk about your center of buoyancy, so sorry center of buoyancy, if I talk about, will coincide here, will coincide with CG of body if and only if your body is submerged body is homogeneous. Homogeneous. So in case of homogeneous bodies, your center of gravity generally lies on their geometric centers. Okay, because here, like, we consider this density of, okay, one more thing, the density of fluid here we consider. Okay, this is also density of fluid, density of fluid, density of fluid, density of fluid. Okay, this is also your density of fluid. Okay, so now let's talk about your buoyant force on in case of a floating bodies or partially submerged bodies. Buoyant force on a partially submerged, or we also call this floating bodies. Floating bodies. Okay. So if I talk about floating bodies, so what happens in your floating bodies is your entire weight of the floating body, entire weight of the floating body must be equal to your buoyant force. Buoyant force. Okay. So FB is equal to weight of the body. Okay. So if I draw a diagram here, so let's say that this here is a water surface. Okay. And this is, let's say, free surface here, and in this water surface we have submerged a body. So let's say this is your floating body, or let me draw it like this, something like this. Okay. Okay, so this is your floating body, let's say. Okay, so in this case, what will happen, like, let's say this is your CG of the body. So at CG, your weight of the body will act. This is your weight of the body. Okay, and at the geometric center of this displaced fluid, that will lie somewhere here, or let me draw, that would be somewhere here. This is your center of buoyancy. Okay, so at this place your buoyant force will act, your FB will act in upward direction, and here your weight will act in downward direction on CG, weight W. Okay, so from here we can say that weight is equal to FB for the system to be be in equilibrium. Okay, and if I in last lecture we studied about your hydrostatic force. So if I compare my hydrostatic and buoyant force, so let me mention it here somewhere. So buoyant and hydrostatic forces are both occur or both caused by pressure only. Okay, caused by pressure only. Okay, but your hydrostatic forces acts on, sorry, I mean hydrostatic forces is a variation of pressure on surfaces, variation of pressure on surfaces, on surfaces, while buoyant forces, buoyant forces, uh, your variation of pressure, pressure on a volume, on a volume. Okay, so this is difference between your hydrostatic forces and buoyant force. So buoyant force is your force on the volume, and hydrostatic force is the force on a surface. So if I talk about your like net hydrostatic force on this your submerged body, so net horizontal force if we talk about, so it will act from all directions. Okay, and it will be cancelled out to become zero. Okay, and here also in your partially submerged body also, although like it will act in different direction, but your net summation in the horizontal direction would be equal to zero always. Okay, because if it's not equal to zero, your body will start to move in a particular direction. Okay, okay, so from here what we can write that my buoyant force, we know that buoyant force is equal to rho of fluid times of g times of your volume of fluid displaced. Okay, or volume of submerged body, and this will also be equal to your density of body, times g times volume of body, that is weight. Okay, so buoyant force is equal to your density of like your weight of the body. So I hope you get this point here. Now with this using this point, we can see here, we can see that if we compare both this and this, so from here we will obtain that my volume submerged, or let me write it with the blue color only. So volume submerged divided by volume of body is actually your ratio of density of body to density of fluid. Okay, so if I consider three different type of bodies, so let me draw a figure here first. So let's say that this is a free surface of water, and this is your like bottom. Okay, now we have three types of, let's say, body here. Okay, let's say one body is floating. Okay, and one body is your submerged, and one more body is your sinked, it is sinked in. Okay, so let's say this is a body A, body B, and body C. Okay, let's say that density of fluid is rho F is the density of fluid. Okay, okay, so this body here we can say it to be your floating body or partially submerged body. In case of B and C, both are your submerged bodies, but this B is your suspended body. Suspended body, or we can also call it as like a neutrally buoyant. Okay, and this is your sinking body. Sinking body. So buoyant force on your both B and C will be same, because volume of fluid displaced will be same in case your all fluids have, all three bodies have your same density. Okay, so from here I will write for all three cases, for A, for B, and for C. Okay, so in case of A, I can say that row of body, row, like here we can say that this is this V submerged upon V body, like V body is complete and V submerged is only this part, so this is less than 1. So it means that this part is less than 1. It means that this part is also less than 1. So row of body must be less than your row of fluid. Only then like your body will float. If your density of body is less than density of fluid, only then your body will float. Okay, if your density of body is equal to density of fluid, then what will happen? If your density is of body is equal to density of the fluid, so your body will be suspended body. Okay, like your both buoyant and weight are equal. Okay, your body will be suspended somewhere in between in the liquid. Okay, now in case of C, if your density of body is greater than that of density of fluid, in that case what will happen? Your body will start sinking. Okay, because there is like net downward force of due to the weight of the body. Okay, your weight of the body is more than that of your weight of the fluid displaced. So I hope you get all these three cases here. So in this based on these conditions only, we generally actually consider your air balloons. Okay, so let me mention a point here. Your density of your ideal gas ideal gas is proportional to is proportional to null to molecular mass or molecular weight, molecular weight of the particular gas. Okay, so your hydrogen and helium are less dense than oxygen and nitrogen or other gas on oxygen, nitrogen, etc., or other gas at same temperature and pressure, same pressure same pressure and temperature. Okay, so this is the reason. And even hydrogen is less dense than helium, but due to hydrogen is highly flammable, it is less widely used, and helium is your inert gas, so it is widely used. So this is the reason. Hence your helium is used extensively for tilting for balloons lifting balloons. Okay, so I hope you get this point. And one more thing, like in case of your like here I mentioned entire weight of the floating body must be equal to the buoyant force. This equation is also known as your principle of flotation. Principle of flotation. Principle of flotation. Okay. Now if we talk about now let's talk about your types of equilibrium. Types of Okay, so types of equilibrium. There are basically three types of equilibrium. First one is stable, then unstable and neutral equilibrium. So let me mention them here. First one is your stable equilibrium. So let's say this is a curvature, okay, and there is a ball which we have kept here. Okay, so let's say this is a ball. Okay, now if we move this ball, if we move this ball, let's say to this position, okay, then what will happen? This ball will automatically return to its original position. Okay, so in stable equilibrium, your body will stop at its original position. Okay, now if you talk about your second type of equilibrium, let's talk about your unstable equilibrium. Unstable equilibrium. Okay, so for unstable equilibrium, let's say that we have a curvature like this, and there is a ball which you have kept at your. Let me do it here again. Okay, let's say this is your a ball is kept at the peak. Okay, now if we move the ball on either side, what will happen? Your ball will fall, continue to fall. Okay, here it will return, here it will continue to fall. On either side, if we move it, it will continue to fall. Okay, so if we talk about unstable equilibrium, so your body will neither stop nor return to their original or to its original positions. Okay, now let's talk about third type of equilibrium, that is neutral equilibrium. Neutral equilibrium. So let's say that we have a surface that is flat. Okay, so your surface is flat. Okay, and if we keep a ball, we have kept a ball on the surface. Okay, now if we move the ball, okay, so let's say we have moved the ball here, so ball will stay here at this location only. So your neutral equilibrium, your body will stop, but not at its original original position. Okay, now these three type of equilibrium are there. Okay, now we will talk about the stability of submerged and floating bodies. stability of submerged submerged and floating bodies. Okay. Okay, so your stability can be like both vertical stability for your floating bodies under your vertical deflection, okay, or your submerged body under your vertical deflection, and your rotational stability in case of your both submerged and floating bodies. Okay, so let me mention some points here. So if we talk about your floating bodies, so stability, or let me mention like this: a floating body under vertical vertical deflection vertical deflection is an example of is an example of. So tell me what will happen, like if you there is a floating body and we have like let's say pushed the body down in downward direction inside the water. So what will happen? Your fluid displaced will amount of fluid displaced will increase, your weight of fluid displaced will increase, okay, but your weight of the body remains same. So there will be a resultant upward force, okay, and your body will come back to its, after removing the load, your body will come back to your uh, original position, okay. So this happens in your stable equilibrium. Example of stable equilibrium: stable equilibrium, okay. Now if I talk about your a floating body under horizontal deflection, so a floating body under horizontal deflection horizontal deflection is an example of. So if we displace the floating body horizontally, so what will happen? Like wherever we keep it, that body will remain here, same there only. Why will it be like this? Because your net force will be equal to your buoyant force in case of the floating, but there is no change in your any type of both of these forces. Neither the weight increasing nor is your buoyant force increasing. Okay, you are just moving the body in sideways direction. So net force in sideways is always zero. Okay, is an example of neutral equilibrium. Neutral equilibrium. Okay, so let me highlight this portion word. So floating body under vertical deflection is your stable equilibrium, okay, and a floating body under your horizontal deflection is your neutral equilibrium. Okay, I hope you get this point now. And now if we talk about your under, like, this is your deflection, vertical deflection, this is these two combined is also known as your translation or linear stability of the system, okay. So if we talk about your rotational stability, so for rotational stability we like for both your submerged and partially submerged body will be different. So let me start here. So let me put a heading here first. So this is a heading, rotational stability. Rotational stability uh, of a completely submerged body. completely submerged body. Okay, so this is your topic. Here we will starting. Okay, so if I talk about rotational stability, so first let's consider the body first. Okay, so let me draw a diagram first before that. So let's say that like this is your fluid surface, of course. Here it is your fluid surface. Okay, and there are three bodies inside your inside this fluid. Okay, so let's say one is this body. Let me make it white color. Okay, this is your body one. Okay, now I will as I mentioned earlier, there are three bodies there. Okay, so these three bodies we are talking about here. Okay, so in these three bodies, let's say that so this is a fluid. Okay, okay, up to this point we have fluid only. Okay, so in these bodies, what is happening, let's say there is a additional weight here. Okay, this is your additional weight. Okay, and this body is like this only, and here this is your additional weight. This is your weight. Okay, this is also your weight. So what will happen here now, if we talk about your center of buoyancy and center of gravity, so your geometric center of this circle will still be your center of buoyancy. Okay, and from here we will obtain a vertically upward force of like FB, buoyant force. Okay, again here also, like this point is your center of buoyancy, and your vertically upward force will be your FB. Okay, here also your geometric center point, this is geometric center point, and this is your upward force. This is your upward force. Okay, and this is your FB. Okay, this is your point is B. Okay, now if I talk about your weight, so since there is additional weight here, so in downward direction here we will have some extra weight W. Okay, and this point is your G. Now here G will coincide with your B, because like the body is homogeneous and like your B and G will lie on the same point here. Okay, because body is homogeneous. Here your weight is upside, like in upward direction or upside. So your gravity, center of gravity will lie somewhere above your center of this circle or sphere, and sphere or cylinder we can say. And at this point, let's say this is point G. Okay, and this weight acting on this point is, let's say, W is the weight acting on the point, and here W is the weight acting here. Okay, so these are three cases. Now if we look into each case, okay, let's say that we are disturbing all these three forces there. Okay, so what will happen? So due to the slightest deformation, let's say we have rotated this. Okay, so due to rotation, what will happen? Your G point, like your center of buoyancy, will be at the center of this circle only. Okay, because this represent your like your center of the water displaced. Okay, so since water is homogeneous, so this will remain at this point only. But your weight will shift. Like if you rotate it like this, so weight will shift somewhere here. This will be your weight. Okay, after like this point will be your G will move G will move to this side. Okay, G will move to this side. So now what will happen? Like since we have like this is your torque, so a restoring couple will emerge from here, and this like FB is upward and weight is downward, so restoring couple is like this. This is your restoring couple. Restoring couple. Okay, so this body will regain its both torques are in a couple are in a positive direction. So this body will regain its original state. Okay, so this is the example of stable equilibrium. Stable equilibrium. Okay, now here if we look into this, so no matter how we rotate this, okay, there is no restoring force. No restoring force. No restoring force. So what will happen? This will be in your, like this is your stable, this is your neutral equilibrium. Neutral equilibrium. Okay, and this here, if we talk about this, so let's say we have disturbed it by some small angle, so what will happen? Your center of gravity will move into this direction. Okay, so your weight will act now here. Okay, weight will act at this point. So what will happen? Your couple is generated in this same direction. Okay, so this is your disturbing couple. Disturbing couple. Okay, so this is example of your unstable equilibrium. Unstable equilibrium. Okay, unstable equilibrium. Okay, so if we talk about, like if I want to write your conditions here, so I can say that this stable equilibrium means that your B must be above G. Your neutral equilibrium, what does neutral equilibrium means? Neutral equilibrium means your B and G coincides, and your unstable equilibrium means your G or B is below G. Okay, I hope you get this point here. So in case of a completely submerged body, if your B lies above G, then it is your stable. If your B lies above G, it is your stable equilibrium. If your B and G coincide, then it is neutral equilibrium, and if your B is below G, then it is your unstable equilibrium. Okay, these 3 points you should remember. Okay, B is above G and B and G coincides. B is below G. Okay, I hope you get this point. Now we will talk about our next topic, that is your rotational stability for partially submerged bodies. For your partially submerged bodies, or you can also say floating bodies. Okay, so we will take some examples here. So let's consider here first a free surface first. So let's say that here it is we have a free surface here. Okay, so this is your free surface. Okay, now we have let's say a boat, or let's simply consider your a floating body example. Okay, so let's say that this is a floating body. We are considering it as, now let's say that this is a your body. Let's say this is a hull of a ship. Okay, and now we will be drawing it once more, but here this is the same location, but we will be tilting it by a small amount. Okay, this is your, we are tilting it here. Okay, sorry about that. We are tilting it here. Okay, now again, and we will be tilting it. Okay, so now we are tilting it. Or let me like make some more space here. So let's say that okay, forget about this. This is your tilt. Okay, now in next figure we are tilting it some more than that. Okay, so let's say this is our tilt. Okay, and we will be drawing one more figure. Okay, and let's say that here we are tilting it even further. Okay, so we are taking these three examples here, and we will see. Okay, and one more thing, like it will, I hope I think it's okay with this. Or let me move these figures somewhat upward. So here let's consider this figure. Okay, now what I can write here, what I can say here, there are a few points I would like to mention here. And of course yeah, if like there is a water level here. Okay, the ship hull is in water. Okay, now we will I will like point your center of buoyancy and center of gravity at this in this. Okay, so let's say that your center of buoyancy is at this point. Now this here like your submerged part and the centroid of submerged part will be indicating your center of buoyancy point, okay, and the force will be your FB in upward direction. Okay, and if I talk about the weight, so weight will act on the like CG of the body. So let's say this is your G point. Now this will be your weight. Okay, now we are tilting this ship. Let's say that ship is tilting in this direction. Okay, so what will happen? Your G will still remain here at this point only. Your G will remain here. This is your G, and your weight it will act in this direction, weight. Okay, but your buoyant force, if I talk about, so buoyant force of the displaced fluid will move, like let's say somewhere here, because like here your like ship your fluid displaced on this side is decreasing and this side is increasing, so it will move, let's say somewhere here. Okay, let's say this is your buoyant force point or center buoyancy, so this force will be your FB. Okay, similarly like here also, like we are tilting it somewhat more, so again your G will remain here only. This is your G, and your weight will act in downward direction, perfectly downward direction. This is your weight W. Similarly here also your G point will remain same, and your W will act in downward direction. Okay, now your center of buoyancy, if I talk about in these two figures, let's say the center of buoyancy is acting here. This is just like the center of buoyancy. Okay, and your, don't go on your like geometric. Okay, so let me make it somewhere here. Okay, so let's say this is your center buoyancy B. Okay, and this is your upward force FB that is acting on the ship. Okay, and here let's say in this case this here is your center buoyancy, and the buoyant force FB is acting here. Okay, now if we like we can say that on this line of symmetry, or we can say that this is your normal axis, this is your white line is your normal axis. So your weight is always acting on a normal axis, but your center of buoyancy is moving like away from your, or is not on the center of buoyancy in case of your tilting motion. Okay, when like your ship is tilting. Okay, so what will happen? So like to study this, we have defined a new concept here, and that concept is of your center, meta center. Okay. So what we generally do, we generally extend your line of center buoyancy, line of buoyant force actually. Okay, and okay, so let me also increase this one. I hope you understood the gist of the gist of this part. Okay, so if I think you guys should have gotten the gist of this part, what I am trying to mention here. Okay, so although let me make some this line somewhat slant, but this line basically straight line. Okay, and the point where this line intersect here is called your meta center, that is represented by m. Okay, and similarly here also we will draw a line. Okay, and this will like coincide with your point G. Okay, here also we will extend the line, and this, let's say, intersect here. Okay, so this here is also your meta center, this here is also your meta center, and this point here is your meta center. Or if I want to, let's say, write your meta center with different color, this point here is your meta center M, this point here is like indicating both G and meta center M. Okay, also your metacentric M. Now here this point will be indicating your metacenter M. Okay, now we will see that what is the reassuring torque, that is how is the reassuring torque acting. Okay, so in this case if we talk about so here let me select some color here first. Okay, so what is happening here, like this weight is acting downward direction. So if we see here, so this will be your like coupling this direction. Okay, so it's tilting in this direction, and couple is restoring couple is in this direction. So this is your restoring couple. Okay, here if you see, so there is no couple. Okay, there is no restoring couple, no restoring couple. If we talk about here, so here your like in this direction, this will be your disturbing couple, because it will further disturb the system. Okay, disturbing couple. Okay, so if I want to say like what is the type of equilibrium in these figures, so I can say here that this system here is in your stable equilibrium. Stable equilibrium. Here this system is in neutral equilibrium. Neutral equilibrium, and this system is in your unstable equilibrium. Unstable equilibrium. Okay. Okay, now in case of stable equilibrium, from here we can say that your M is above G. M, your M above G, your M and G, M and G coincides. Okay, and your unstable equilibrium, here what is happening, your M is below G, M below G. Okay, so M above G is very stable, M and G coincides is your neutral, and M below G is your unstable. Okay, now let's define your metacenter first. Okay, so your meta center, which is indicated by your metacenter, which is indicated by using your M. Okay, is defined as, this is point of intersection of normal axis and new line of action. Let me move it in below line. New line of action of buoyancy force. Okay, so this is your metacenter. Now, so this metacenter is also like your it is also your point about which your floating body, about which floating body oscillates or oscillates when given small displacement, small disturbance, or I can say disturbance. Okay, like and disturbance is your angular type of disturbance. Okay, so this metacenter is basically your this metacenter is your point about which your floating body will oscillate. Okay, this is your center. Okay, now this distance between G and M, distance between GM is also known as your metacentric height. Okay, and this is basically vertical distance between G and M. Okay, and your distance between B and M is your metacentric radius. Distance between B and M is your metacentric radius. Okay, so around M it will rotate, like center of buoyancy will rotate like this, point B will oscillate like this. Okay, now as I mentioned earlier that M above G, MG and G coincides, or M below G, so I can show you this on your like a simple chart. So let's say that this line here represent your center buoyancy point of center buoyancy. So let's say this point here is your B. This point here is also, like, we will consider different examples. Okay, this point is also B. and this point is also B. Okay. Okay. So let me draw your reference line also. There are few reference lines on these points. It's better to draw with pencil. Okay. Sorry about that. This is your, let's say this is your line of action of Buoyant force, line of action of Buoyant force, line of action of Buoyant force, and line of action of Buoyant force. Okay, let's say that now your this is the location of your G. So here, sorry about that, this is location of your G, this is your G, this is your G, and this is your G. Okay, and let's say that your metacentric point varies. So your earlier this is, let's say, your metacentric point. Now here metacentric point is this. Now your metacentric point coincides with your G. Okay, coincides with your G. Now your metacentric point is, metacenter is your below of G. Okay, so in this cases if we say, so as I mentioned earlier, m of G is stable, m of G is stable, but here also that m of G, here m and G coincides, so this is neutral, and here m is below G, that is your unstable. So I can say in this that along this direction, your stability decreases, stability decreases. Okay. Now to determine whether system is on your stable, unstable, or neutral equilibrium, I have already mentioned it here, but let me mention it here also, like combine it into one form. But before that, let me mention one more thing from here. So if you, we see GM here. Okay, so G, if M is above G, so this will be positive. Okay, so we can say that this metacentric height GM can either be your positive, can be 0, or can be negative. Okay, similarly in case of BM also, this okay, but not GM, GM only. Okay, so here what will happen, like in case it is your, in case it is positive, so this is your stable equilibrium, stable. Okay, in case 0, then it is neutral. Okay, in case it is negative, so this case, so this is unstable. Okay, now as I mentioned BM here, so this is BM, this is BG. So from here I can like refer 3 more points from here, and those points are, if your BM is greater than BG, okay, or your BM is equal to BG, or BM is less than that of BG. Okay, so in these three conditions, I can say that in case your BM is greater than BG, like this, so this is stable equilibrium, stable. In case your GBM is equal to BG, so this condition, so this is neutral. Okay, and if your BM is less than BG, so this point is your becomes your unstable. Okay, so these are the conditions for your partially submerged bodies to be stable or unstable. Okay, now from here we can also write your GM, that is the metacentric height I mentioned earlier. So GM, your this metacentric height GM is equal to BM minus BG. Okay, now in Now we will see like we will summarize the stability condition and look into details how to calculate your metacentric height. Okay, let's start. In order to your calculate your metacentric height, determination of a metacentric height. Okay, so there are basically two methods. First method is your experimental 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 method. Okay, so let's consider example first. So let's consider floating device. So let's say that this is your free surface. Okay, and here let's say this is your system. Okay, now okay, but before that let me remove few parts from here. Okay, so this is your body, let's say, and we have kept a weight w, kept a weight w on this. Okay, so let's say that okay, so this weight is here w. Okay, and what we will do now, before that, one more thing. Here it is g, here it is center of gravity of the body, and the weight acting on this is capital W. Okay, so let's write it is here small w, here small w. Okay, and at this point we have, this is your center of buoyancy. Your force Fb is acting here. Now let's say that if we let's say that now what we have done, we have rotated this system here. Okay, so let's say it's something like this. Okay, and your this block is moved by a distance, let's say x. Okay, so let's say that the distance the box is moved is by x. Okay, and at this point your weight will be acting like this. Okay, and your weight w will be acting still at this point, and let's say here. Okay, this is your center of gravity. Okay, now your buoyant force will act, let's say, somewhere here. Okay, let's say that here is your buoyant force acting. Okay, and this is your Fb. Okay, now if we extend this line, let's say it meets up to this, meets up at this point. Okay, but let me, this is your buoyant force, and if we extend the line here, if we extend line here, so it meets at this point, and this point here will be your metacenter, that is your m. Let's say that this angle is your theta, this angle is your theta. Okay, now this is your basically b1, your b1. Okay, your original b was at this point, original b what at this point. The center of buoyancy moves from this point to this point. Okay. So, and the value of this buoyant force Fv is equal to W, that is weight of the ship. We know this. Okay, because this small weight is like included in small weight is included in the weight of the ship. Okay, so what we can say, let's do one more thing. Let's name this point as your G dash. Okay, this will be your apparent point of weight, like if your body was aligned along this point. Okay, so what I can say, that if I take my movement, if I take my movement about this point M, because as I mentioned earlier, that this meta center also indicates that this is your point of rotation, or this is your center of axis of rotation. Okay, so I can say that small w times of the moment created. Okay, this will be equal to your like moment created due to the weight w w times of g d dash. Okay, and due to this buoyant force, your moment will be zero about point M, because it is passing through point M only. So now what we can do from here, I can write that w times of x is equal to w times of, now gg dash, if we talk about this point, taking this triangle gg dash m, so from here we can write that my gg dash is equal to gm times of tan theta, gm times of tan theta. So from here I can write my gm, or metacentric height, is equal to wx by w tan theta. Okay, so this relation you have to remember. Okay, your second method is your theoretical method. Second one is your theoretical method. So according to theoretical method, your metacentric height, this states that your gm is equal to bm minus bg. So we can see this from here. Let me. So your gm is equal to bm minus bg. Okay. Now here, like you have to find both bm and bg. Okay, and your bm value, bm is equal to I upon volume of fluid displaced. Okay, and this I here is least moment of inertia, least moment of inertia of surface formed at free surface. Okay, so we will observe what is the shape of the surface formed at the free surface, and for that we will calculate least moment of inertia. It is also called your waterline area. Waterline area. Okay, and your this is your bm. Okay, that is your metacentric radius, and your bg is like calculated geometrically. Okay, so like we will measure from b to g distance. Like if you are generally in questions, your shape of the object is symmetrical, like either cubical shape or cylindrical shape. So there we can generally calculate distance between b and g. Okay, now let's talk about your ship in a water. Okay, so let me draw a ship first. So let's say that this is your free water line. Now this is the hull of ship. Okay, and here I am drawing your water line area only. Okay, okay. Similarly here also it would be something like this. Okay, okay. Now so this is your ship body. Okay, this is your ship body. Here also this is part of ship body. This is also part of your ship body and is called your hull of ship. Hull of ship. Now one more thing I would like to mention here, that is your there are three axes basically. If we look into this, so there will be three axes. So let me move it downward first. So let me mark the axis of a few axes here. Okay, so one is this axis. This is your longitudinal axis. Okay, this is your one of the axis. This is your other axis, and your this axis, your vertical axis. Okay, okay. Now this axis is called your foreaft axis. Foreaft axis. Okay, and if we talk about the rotation in this, so this rotation is called as your rolling. Okay, now if we talk about your rotation or not rotation, basically your movement like this, so this is called your sway. Okay, now if it is like moving or rotating around this axis, so this is your pitching. Okay, and this is your, if it moves like upward and downward, so this is your heaving. And your moving forward is called as surging. And this rotation along this axis, rotation along this or rotation in this surface is your yawing. Okay, so if I name this, let's say this body is your xx, here this is your yy, and this is your, let's say, zz. Okay, so what I can say, I can write my ixx is equal to, let's say this is your b is the width and l is the length. Okay, so blq by 12. Okay, your iyy is equal to lb cube by 12. Okay, and from here I can write that my bm for xx direction is equal to ixx divided by v, of course fluid displaced. Similarly bm along yy will be your Iyy upon vfd. So from here we can see is like, since your ixx is greater than that of your iyy, so from here I can say that your bm for xx is greater than that of bm of yy. Okay, and from this we can what we can say, we can say that your bm for along axis is your pitching, so bm for pitching is greater than that of bm for rolling. Okay, so we see that bg is equal to bm minus bg. Okay, and your bm of pitching is greater than that of bm rolling. Okay, uh, so if we substitute here, so we can write from here that gm in pitching is greater than gm on rolling. Okay, so from here what I can say, I can say that so we must always design ships or design, okay, ships on basis of least moment of inertia, okay, or I can say that in rolling, if I like make it design suitable for your rolling, then it will always it will automatically be stable in case of your pitching. Okay, so or rolling, because if gm is positive in rolling, it will be more positive in pitching. Okay, so this is why we use your least moment of inertia. Okay, and in ships we generally solve it for your in like make it stable for your rolling, then it will automatically be your stable in case of pitching. Now let's talk about your time period for oscillation. Time period of oscillation of floating bodies. Okay, so your relation is given by t is equal to 2 pi times of root k square divided by g times of gm. Okay, so from here I can say, oh okay, but let me mention what are these terms. So k is your radius of gyration, and gm is of course your metacentric height. Okay, so from here what we can say, like your time period is inversely proportional to your inversely proportional to 1 by root of gm. Okay, so if we consider, let's say that you are sitting on a pendulum. Okay, now if the pendulum time period of pendulum is, let's consider two scenarios, that is your one at one place your time period of pendulum is small, and at another in another case your time period of pendulum is large. Okay, let's say that for first pendulum your time period is 1 second, and for second pendulum your time period is 10 seconds. Okay, so what will happen in case where time period is 10 second, you will feel more comfortable. In case your time period is 1 second, your comfort level will be low. Okay, so from here what I can say, I can say that if gm value is very high, what does it will it indicate? It indicate that stability. Okay, stability will be higher stability, we know that. Okay, now if gm value is high, what will happen? Your time period will be, and time period will be low value, time period will be low. Okay, second, if your time period is low, time period is low, then what does it mean? This mean that your level is low. Okay, so for higher comfort we need your lower value of gm or metacentric height. For higher stability we need higher gm. Okay, so we have to optimize the gm value for to obtain it between obtain it such that your comfort and stability both are proportional. Okay, so if we talk about your passenger seat, passenger ships, passenger ships, and let's say second your warships, warships. Okay, so in case of your passenger ship, we can see? We can say that your gm is optimized, metacentric height is optimized to like uh, obtain your optimum comfort and stability. In case of warship, your comfort is secondary choice, your stability is the higher choice. Okay, so your gm is very high, very high, so it would mean your time period is less and comfort is low. Okay, I hope you get this. Okay, now as I mentioned earlier that I will review a summary of your stability for submerged and partially submerged bodies. Okay, so let's talk about it here. So this is your summary here. So here I can say that for submerged and floating bodies, when b is above g and b is below g. Okay, so for submerged bodies, when your b is above g, it is stable. Your b is below g, then it is unstable. Okay, but in case of floating body, if your b is above g, it will be stable. Okay, if your b is above g, so whether it is submerged or floating, your body will always be stable. Okay, now problem arises when your b is b is below g. In that case, what happens? Your submerged become unstable. But in case of floating, if your m is above g, then it is stable, and your m is below g, then it is unstable. We replace here b with your m. Okay, so your m is above g, so it will become stable. M is below g, so it is unstable. I hope you get this. Okay, now there is one more topic I would like to discuss here, that is your loss of weight due to buoyancy force. Okay, loss of weight due to buoyancy force, buoyancy. Okay, so what happens? Let's say let's consider two conditions. Let's say this is a ball, okay, and it is connected with a weight measurement device, okay, with a weight measurement device, okay. Again, let's consider the same diagram, okay. Now here your medium is air, and this is your in your water. Let's say this ball is kept in here water, okay. Your tension here, like if you talk about ball, so in the ball your weight will act in downward direction, okay. Your buoyant force will act in upward direction. This will also happen here, okay. Your buoyant force is in upward direction and your weight in downward direction, okay. Now here your tension will be T, here your tension will be, let's say, T1, okay. So what I can say here, that your T is will be your reading of the your this, okay, spring balance. This is your spring balance basically, spring balance. So T, here your T will be your weight minus FB, okay. And what happens in case of your air, in case of air, this will be similar to 0, almost equal to 0, because density of air is very less, and in comparison to weight it will be very less. So T is equal to weight, and this is also known as your true weight, true weight, okay. Here if we talk about, so your T1 will be reading of the spring balance, and this T1 is equal to your weight minus FB. Now here, since your medium is water, so your FB will have certain your like your like quite the value, okay. It cannot be neglected with respect to your weight, okay. And this term is also known as your apparent weight, apparent weight, okay. So your loss in weight, so from here we can say that our loss in weight is equal to your true weight minus apparent weight, T minus T dash, and this is equal to your buoyant force. If we subtract both, so I will obtain this value is equal to your buoyant force. So loss in weight is equal to your buoyancy force, okay. And while measuring your body must be immersed in a single fluid or only, okay. Like it shouldn't be like the body is floating and you are measuring the weight. In that case your weight won't be actual. So with this we have concluded our chapter buoyancy and flotation. So thank you.